Okay, so finite state machines. Let me find my arrow keys. All right, so what is a finite state machine? Well, it's a form of artificial intelligence. It's a programming pattern where a part of your program will change its behavior at runtime depending on certain conditions. And that behavior that it is in is based on what state it is, and it can be in one of any finite number of states. What's also nice is that the states themselves contain the conditions and the code to transition to another state. The most basic example of this is, of course, a light bulb. A light bulb has two states. You flip the switch, it goes to the on state, and there its behavior is to emit light and heat. You flip the switch again, it goes to the off state, where its behavior is to not emit light and heat. A really common example of this also is the artificial intelligence for in video games for the enemy. Generally, you can have something like the enemy starts with this in this patrol state where it's just wandering around aimlessly, but then it sees the player, and that is the condition that triggers its transition from the patrol state to the attack the player state. And then once the player is dead, or the player, say, leaves the visual range of the enemy, then those are the conditions that trigger it to go back to the normal patrol state and resume just walking around aimlessly. So some of the advantages are that finite state machines are relatively quick and easy to code. I'd say they're at the 110C, 111C level. You need to know templates if you're using C++, or generics and interfaces if you're using Java. And you also need to know inheritance, which is taught in 110B and 111B. It also has the advantage that it has relatively little overhead is required. It doesn't take a lot of computational power because these things are ultimately if-else statements on crack, sometimes within a game loop or a while loop. They're also really flexible. If you want more behaviors, more different behaviors, you can just add in more states. You can also do some weird stuff with the states and make different kinds of finite state machines, and I'll give you an example of that later. So they're pretty useful. So let's talk about how you program one. Well, first off, your class, just kind of looking at this diagram here, this is a diagram for the state design pattern, which is pretty close to what we're talking about here. Your class, your game AI, or your enemy class, or whatever else is in your program that needs the finite state machines, needs the different states, is going to have an instance of the state machine class. And then it also is able to reference the own states. So you can see here this is the state machine class, and here's the state class. And let me just talk about this first. So the state class is going to be a template, or if you're using Java, it'll be your interface. That means that it really only exists for other classes to inherit from. The key thing here is that you have these three void methods: enter, execute, and exit. And those are important when you create the own state class. This is where you'll actually write the code that talks about what the enter, execute, and exit functions do. The enter and exit functions you don't really need them, but they're nice as sort of a prep work or cleanup when you're entering and exiting a state. Most of the legwork is going to be in the execute function itself. So you can see here in this example, here we have state 1 in the enter function. It just says, puts out it's getting ready to do stuff. The exit, it just says it did some stuff. And then in the execute is where it will actually be doing whatever stuff it is. The execute function is also going to contain the criteria to switch to the other state, as well as it'll call the function to switch to the other state, to whatever the next state is. So here in this example, it calls a function from state machine called change state, saying, okay, it's time to change the state to state 2. That's the parameter that it passes in. Now the state machine class, I'm not going to show some code for that because everyone's eyes will just kind of glaze over, mine included, is also going to be generics, a Java generic or a C++ template. But the key things that you need are, you need a pointer or a reference to the class that owns the state machine. That way, if something happens in the state that changes the class, this is how it's able to pass on that change. You also need a variable for the current state. It needs to be able to reference what state it's in now. Previous state is kind of a nice to have thing, just in case you need to flip back to whatever it was in before. And then global state is something that is useful for when you add in more features. The global state, that function gets updated first, so it's nice if you need to interrupt the normal flow of things. Then you also need an update function or a handle function. That is going to be what calls the execute from the owned states. And that'll happen once every, if you're doing, say, a video game in the game loop, then each time going through the loop, the update function gets called. And then it calls the execute for whatever the current finite state machine is. And then you have the change state function that I talked about in the previous slide. And the change state function is going to call the exit and enter functions as well as change what your current state is. So say, going back to this, if we're going from state 1 to state 2, what the change state function will do is first it'll call the exit function for state 1, and then it'll call the enter function for state 2, and then last it'll change the current state from state 1 to state 2. And then that way next time update happens, when it updates the current state, it'll run the execute function from state 2. And then also you need to have getters and setters, get current state, set current state, and so on and so forth. Now, I mentioned that you can do some weird variations of finite state machines. Well, I'll show you here an example. You can have this whole stateception thing going on. Hierarchical finite state machines. So you have two states. You have doing the job and spinning the top. And these are at the same level in the hierarchy. So they're equal. They're of the same rank. But within the doing the job state, you have three finite state machines within it. You have diving in a level deeper, fighting some dudes, or finding the guy. And so you can go through all of those, but then let's say at some point, the spin the top state gets activated. Because the spin the top state is at a higher level in the hierarchy than these, it immediately stops what it's doing and it goes on to spin the top to see if any of this is even real. And then once it's done with that, it goes back to the doing the job state and picks up wherever it was that it left. So a hierarchical finite state machine is good if you have some sort of interrupting behaviors. So, if you've ever played a game where there's an NPC just roaming around, but once the action starts, the NPC runs and hides, well, that would be an interrupting behavior. It runs and hides until the danger is past. So that's an example of that. So I have a demo that I'll show, and I pulled this from a personal project that I've been working on. It's going to be, you'll see it's a class that is essentially a Afghan-style insurgent cell. And it has 5 states. It has a global state, but in the global state here, it doesn't do anything. In the original program that I pulled this from, the global state does stuff. But of the remaining 4 states, first you have the default state is the drink tea state. This is when our insurgent is just sitting around drinking tea. From there, I use a random number generator. And so there's a 1/3 chance of it to continue drinking tea, or it can go and intimidate the villagers, after which point it returns to drink tea, or it can go and conduct an attack, which I also have another random number generator to say if it's bombs or bullets, after which point it returns to drinking tea. However, the class has an integer that I use to store how much supplies the insurgent still has. And so after every 2 attacks, he runs out of supplies. And so instead of going back to the drink tea, he goes to the resupply state, which will then increase that integer back up to full. And then he'll move on to drink tea. So let me show you that so that you can see kind of what I'm talking about. All right, yeah. And we need to come up with a name. I'm going to call him, Little Timmy. All right, so he starts off in the drinking tea. So, and there's the message that he says. All right, wait, I didn't mix the green tea with the black tea, did I? Now, he decides, based on the random number generator, that he's going to go and intimidate the villagers. And so this is when it's the enter function for the intimidate population is to just print out that. Time to show the unwashed masses who's boss. All right, so he steals all the lunch money from the villagers, and then the next one, that'll learn him. That's the exit function for the intimidate population. And so now we know that he's going to go back to the drink tea. So saying that being insurgent's thirsty work, that's the enter function for drinking tea. I forgot to code an exit for drinking tea, so you won't see anything indicating that it's there. So next, for the next iteration, we should see him drinking tea, followed by an enter function for whatever the next state will be. All right, he's going to intimidate the people again. Yep, going back to the tea. Okay, now he's going to attack. All right, it was a bomb, and he's going back to the tea. And he's going to attack again. So now, because this is going to be his second attack, once he's done with that, he's not going to go back straight to drinking tea. He's going to go and resupply. See, so he's all out of bullets, sad face. And he gets back his bullets, and he goes back to drinking tea. And so you can just go on with this forever and ever and ever. Oops. All right. So the next step from there, like I said, there's all sorts of weird stuff, fuzzy state machines, hierarchical state machines. For anyone who was here last week with Joe Allen from Glue, he mentioned something really interesting, which was one of your states could be a behavior tree. And a behavior tree is a completely different type of AI implementation. So basically, it's a really deep rabbit hole. You can end up in some really interesting places with it. Would you like to know more? So there's the GitHub. I forgot to write it down on the dry erase board. I'll write it down later. That has the code for that finite state machine demo. The Rosenberg Library here on campus has a book, Design Patterns, Elements of Reusable Object-Oriented Software. This is a book that's referenced a lot in the computer science world called the Gang of Four, commonly called the Gang of Four book. And they have about a 10-page section on the state pattern. However, it's pretty dry reading. So another alternative is this book, Game Programming Patterns. You can find the whole thing for free online, but I have a hard copy that I purchased here if anyone wants to look at it. He has a section on the state pattern, so you can see about finite state machines. And then lastly, for the stuff that I'm working on for my personal project, I got the finite state machine state-driven AI stuff from this book, Programming Game AI by Example. And the bulk of the chapter on state-driven agents is available on his webpage, so you can go there and look it up. Does anyone have any questions?